Welcome here today. My name is Sunny Yu. I'm a teaching fellow and outreach liaison at the University of Southampton. And tonight I'll be your host. This event is part of the Southampton Science and Engineering Festival of 2022, organized by the wonderful team of the Public Engagement with Research Unit at the University of Southampton, running from tonight, 11th to the 20th of March. So if you want to comment on any social media about tonight's event, please use the official festival hashtag of #SOTSEF. So I am very happy to be here today. And while I introduce myself, I'd like to be able to see some of the audience we have over here as well. So if you can put in the comments, where are you from, and where you're watching this from, that'll be great. And particularly if there's anyone from between the age of 14 to 17, let me know as well. I'll be excited to meet you through this virtual method. So let me introduce myself. As I mentioned, my name is Sunny, and yes, that's a real name. I am myself a theoretical physicist, and my personal research is about exploring fundamental theories of quantum gravity and cosmology. Personally, I'm really very passionate in sort of sharing the ideas of mathematics and physics, and sharing the joy to as many people as possible, because and this is the reason why I want to start with this topic of special relativity tonight, that it's one of a very dear topic to myself. Even though now myself I am a theoretical physicist, there was a time in my life where both I hated mathematics and also physics at two different points in my life. And there's two different reasons which brought me back to suddenly rediscover the joys of mathematics, and then later on a reason that led me to rediscover the joys of physics. So there's actually two folds I want to achieve with tonight's event for this talk. And this topic of special relativity is really dear to me because it is the topic where, when I sort of completely lost interest in physics and I borderline almost failed one of my high school physics exam, and someone just showed me a book and to read about the ideas of special relativity, and it opened my eyes to completely. I did not know the universe or the world behaves in such a really interesting way. So some of you may have heard of these ideas before, some of you may not, but part of my goal, one, is to share with you some of the basic ideas of this theory, but also hopefully to show you some of the things that attracted me so much, that sort of pulled me in and become really interested in physics, again, towards the end of my high school, leading me to study at university, and continued, and it never ceased to amaze me. It all sort of, my whole theoretical physics journey all started with being introduced to these ideas of special relativity. So it's nice to see a lot of comments started, and well, let's get started in this journey. So today, I'd like to just take you through a brief tour of these amazing ideas in special relativity. And I want to start with this. I want to start with three questions to see what you feel about them. So imagine the first scenario where we have a truck moving at, let's say, it's a very modest speed at 2 miles per hour, and we have a sheep moving on top of it at 2 miles per hour, running at 2 miles per hour on top of the truck. So my question to you, if you would like to put in the chat, is, if you're looking from the side, looking at the speed of the sheep, what do you think the speed is compared to yourself? So you're standing still, the truck is moving, the sheep is moving on top of the truck. What do you think the speed of the sheep is? A, do you think it's 2 miles per hour plus 2 miles per hour? Or do you think it's something else? So put A or B in the chat. While you're thinking about this, let's see. Let me pose a second question so you can start thinking about this as well. Now, let me change it a little bit. If I have a truck and someone stands on top of it and shoot out the speed of light, take a torch, turn it on. So light just comes out, shooting out on top of the truck, which at the speed of light, while the truck is still moving at this 2 miles per hour. Now, the same question, what do you think if you're standing on the side, what is the speed of the light that's coming out from someone who is on a moving truck? Well, here are the options. Let's see what you find in the comments. Do you think it's, well, the speed of light, which is in mathematics, we call it c, plus the 2 miles per hour of the truck? Is it just c, or is it something else? If it's something else, what do you think it is? So let's have one more question. What if this time we have a really fast, some of you may already know the answer to the previous two, but let's see this one. If I have a really fast moving truck that is moving at 75% of the speed of light, so this is sort of a technical way we mathematicians write it as 0.75 c, but that's 75%, so 3/4 of the speed of light, and not, well, a truck cannot move quite that fast at the speed of light, but let's say it's just a little bit underneath. And there's another really fast moving car on top that's moving at 75% of the speed of light. And the same question, if you're looking from the sidelines, what do you think the speed is? Is it just the sum of the two? Is it speed of light, or is it something else? Okay, so this might already start to cause a little bit of confusion. So let's try to dissect some of these ideas. Let's look at back at the second question with just shining the speed of light on top of a moving truck. Now, some of you, if you have heard anything about relativity, you'll probably know that nothing goes faster than the speed of light. So the answer to this is probably just the speed of light. But this is an interesting contradiction, because if you do this, then if you remember, if one of them is moving at a speed of light, 75% of the speed of light, and the other is also moving at 75% of speed of light, and how would I resolve this case? Do I just add them, or does it cap at the speed of light? What's going on? What is the right way to think about the relative speeds between this? So all this is seemingly a bit of a confusion, admittedly. And I want to dissect why we actually struggle with this is because we are kind of, in everyday life, sort of get used to what's called the classical laws of motion, which was developed all the way, very intuitive, that was formulated all the way back in the 18th century by Galileo and Newton and their friends. So a few different ideas that were formulated is, number one, speed is relative. So it's relative to the sheep speed is relative to the truck speed is relative to the ground. So we can ask, what's the sheep speed relative to the ground? And in the past, our intuition tells us that relative speeds simply just add up. Also, it's important to know that when things is moving in a constant velocity, there's no way to tell that the situation is any different. And the technical way of saying that is all the laws of physics are the same when you're in a constant motion, a constant velocity. So if you don't change your speed, if you don't change your direction, imagine you're sitting in a very, very smooth ride, a very smooth train, for example, going through the countryside. There's no vibration. If there's no windows, no black box, if it's just moving in the single direction, you can drink a cup of tea. You can do juggling. Everything on the train, as long as it's moving in constant velocity, everything stays the same. Now, these are the intuitive sort of ideas we are familiar with. What kind of gets in the way that sort of causes the confusion in question 2 and question 3 is in the 19th century, there's this guy called James Maxwell, and he came along and developed the theory of electricity and magnetism. And he discovered that basically light is a wave that it's not instantaneous. It will travel from one place to another place, and it travels at 186,000 miles per second, or scientifically speaking, 3 times 10 to the power of 8 meters per second. So that means, and every second, the light will travel 3 followed by 8 zeros. So that's a lot of zeros per second, right? To give you context, it basically, the speed of light would move around, it would wrap around the Earth 7 times in 1 second. So that's the kind of speed, even though it's very, very fast, it still moves, it's not instantaneous. And this is, all right, this is very fast, but the most contradictory thing, which sort of brings up all the questions, is now we need to ask, because we understand from our previous knowledge, speeds are relative to what? Now, very peculiarly in the equations of what Maxwell discovered was that it's relative to everything. So that's another way of saying the speed of light is sort of nothing can go faster than the speed of light, because if you go back to the person holding the torch on the truck, turning on the torch, turning on the flashlight, the light shoots out of that relative to that guy at the speed of light. It's also the same speed relative to the truck and relative to the person on the ground. Relative to everyone, it's the same speed. Now, this is a stark contradiction to the idea that relative speed should simply add, right? So what is going on? This is caused a lot of confusion for a long time. And finally, we'll introduce our main character over here that we are here for to listen to his theory, is Mr. Einstein. So Albert actually thought about this problem. In fact, he thought about this problem not as the sort of eccentric old man scientist that we often think of, but he thought about this at a very young age. Well, maybe not this young, but in fact, he was start thinking about this exact problem of, do things exceed the speed of light? What if two things are very close to speed of light and they add? Do that exceed the speed of light? And he started thinking about this problem at the age of 16. Right? So if anyone in the audience is between the age of 14 to 17, I don't know what is occupying most of your day, but this is what occupying most of the time when Albert, in fact, he thought about a very particular case. He thought, if I hold a torch and shoot out a beam of light at the speed of light, and if I sit on that speed of light and shoot out another beam of light, will that light be traveling faster than this light, according to someone on the ground, right? And he came to the conclusion that it shouldn't, because if that's the case, if he replaced things with an iPhone, well, I don't know if he really has an iPhone back then in the early 20th century. Probably he was thinking in terms of a mirror, but let's say he's trying to take a selfie or look in the mirror. Well, his question, he thinks of himself at a young age, is, can I see myself, right? Because for you to be able to see myself, for you to be able to see yourself, if you're sitting on a beam of light, the light will have to go from your face to the phone or the mirror, and then it has to reflect, or in the phone, it has to re-eject the light back to yourself. So light must travel faster than the speed of light to go to the mirror. And is that possible? So the question is, can I see myself? What is the right way of thinking about speed of light? So this is the sort of thought experiment which Einstein later became very famous of conjuring up. The thought experiment that really baffled Einstein into thinking about this. Right. So now I hopefully have successfully confused all of you with what is really going on. And let's try to dissect this. And Einstein was the first one who sort of came up with the really ingenious idea of this. How do you really, so at the fundamental level is, how do you resolve this conflict between electromagnetism and classical laws of motion? And his idea was this: well, the newly discovered theory of electromagnetism is saying the speed of light is constant. Now let's assume that's true, because that is sort of he took very good faith on the new discovery of this theory, and there's good reasons for it. And he thought, well, okay, so if everyone has to agree on the speed of light, right? But speed is simply just the amount of distance. It's just the concept of how much distance you cover during a certain time that it takes to cover that distance. Well, if everyone has to agree on the speed, then we must not agree on the idea of distance and time. So when something is moving, if we ever have, this is the you can say crazy or genius idea of, if when something is relatively moving to something else, if everyone have to agree on some speed, then they must disagree on the time that is that is ticking according to that person, as well as distance. All right, so let's illustrate this. Let's sort of flesh this out in a more concrete example. So let's assume we have two spaceships in space. And because of the distance we're talking about and sort of the quick speed of light, so let's sort of introduce another concept first. It's called the light second. So what do I mean by light second? Well, most of us have heard of the idea of light year. A light year is a distance that light travels in 1 year. Okay, so just to remind you, so for example, if there's a flash of light going from one side to another, that distance, if it takes 1 year to travel, that's the distance is 1 light year. Contrary to what Star Wars tell you, it's not time. It's the distance that 1 year it takes. And well, similarly, we don't really want to sort of take years to talk about this. So we can similarly introduce the idea of a light second, which is the distance that the light travels in 1 second. Okay, so there's a certain distance. Just because we're talking about light, it's a little bit easier. All right, we'll talk in terms of light seconds. Okay, so since light travels at 186 miles per second, so in 1 second, basically 1 light second is 186,000 miles. Okay, so that's the distance. So instead of me just keep saying on 186,000 miles, I'll just say 1 light second. So that's the distance we're talking about. Okay. All right. So just to understand how this puts in the context of speed, right? So speed is a distance covered by the time it takes. So speed of light always will travel at 1 light year per 1 year. Right? It takes 1 year to travel 1 light year for light, or it takes 1 second to travel at 1 light second. Right. So that's the speed, 1 light second per second, or 1 light year per year. Okay, so back to our spaceships. Right. So assume that the first one on top is not moving, and the other one is moving at half the speed of light. Okay, how would it affect the time? Let's see. So let's think about them both shooting out a beam of light over a distance of 12 light seconds. Okay, so that's a certain distance. So what will happen? All right, so after 12 seconds, if we look at this, well, after 12 seconds, the lights would have moved from here to here because light travels at 1 light second per second, right? So it takes 12 seconds to travel this distance. And because this second spaceship is going to move at half of the speed of light, so after 12 seconds, it will also have traveled 6 light seconds, so halfway through, right? Half as fast as the little beam of light. Okay, so what is if we are naive about this, what will we measure? Well, this guy, if you're an astronaut looking out at this beam of light, you will see the light has traveled 12 light seconds, a distance of 12 light seconds in 12 seconds, according to your clock. But if you're this guy, you don't know that you're moving because you're moving at a constant speed. Throughout this process, you're moving at constant speed. So everything looks the same as you. Looks the same to you, and you just see that according to the ruler, you just looked over here and see that, well, there's only 6 light seconds between myself and the light beam. So it looks like the light between the starting point and the ending point, it only covered 6 light seconds in 12 seconds. So that clearly is not correct because now I'll calculate the wrong speed of light. My speed of light is smaller than what it should be. Well, here's what Einstein's genius idea is. What if the time slows down? For example, what if you don't move, the clock on your watch would run for 12 seconds, but if you do move, according to the other person, your clock will only run for 6 seconds. It slows down. If that's the case, then you will calculate the speed of light as, well, it traveled for 6 light seconds, according to my measurements, from the head of my spaceship to the end of where it ends up in 6 light seconds in only 6 seconds. So everything will be fine. Now I'll have the correct speed of light. Right. So that was Einstein's idea that time will slow down as much when you move. Well, this sort of prompt is the motivation for him, but that doesn't really explains why time is slowing down, right? So let's see if we can understand, actually go to the bottom of this and think and figure out why is that true? Well, we first have to ask ourselves, what is time? And the answer to that is it's something periodic, right? So if we go back to prehistoric times, what do people consider as time? Well, maybe the time it takes for the sun to go from to rise from one side to another, one cycle, right, to come up again, and we'll call that one day. We can surely split the day in 24 hours, that's fine. But anything that periodic, if it moves, we realize the sun shows up on the east periodically every day, right? So we can use that as a measurement of time. It's not the most accurate because we know a day sort of increases and decreases in length. So that's not the most accurate thing, but historically, that's the first thing people think about. If you use the idea of the Earth moving around the sun in a whole orbit, going around for 1 year, so you look at the seasonal change, the periodic seasons change. So you have spring, summer, autumn, and winter, and it comes back to spring again. Looks like everything repeats. Now you have a larger time scale and you subdivide that into 365 days. Then you can sort of get a little bit more accurate idea as well. But anything periodic essentially can be a measurement of time. If we still remember what our grandfather clocks with a pendulum swinging back and forth, that can be a way to measure time. And of course, those are more precise measurements. But none of those are the most precise way to measure time. So let's introduce a foolproof way that makes sure everyone agrees on how we measure time, and it's called a light clock. So what is this? Is imagine I will send the light back and forth between two mirrors. So this is something periodic. You just sort of have a little piece of light bouncing up and down, back and forth like this. And because everyone agrees on the speed of light, right? So we can now agree on for example, however many bounces constitute 1 second, right? We can just define a number of bounces. That is what we'll call 1 second, right? So there's a specific number. Well, it depends on how far your mirrors are. But if we define some standards, then everyone can agree on this is how we measure time, right? X amount of bounces is 1 second. All right, so let's say this is the most accurate way to measure time. So let's put a light clock on both of our spaceships. This one is not moving, and this one's moving at 50% or half the speed of light. Okay, at 50% of the speed of light. Now notice because light travels the same speed for everyone, according to Maxwell's latest discovery back then in the 19th to 20th century. You see that if this is a moving clock, this light has to travel a diagonal path compared to a standstill clock. If this were to bounce up and down, right, it has to bounce up and down between the two mirrors. This will have to travel a little bit longer than a clock that is standing still. And that is the reason why light or time, as a result, is slower, because light takes longer to bounce between them, right? So this was a great discovery, and this is, believe it or not, this is something that is actually measurable and how the universe works. The moment you jump on a train, the moment you jump on a car, a bicycle, even if you start walking compared to someone else, imagine you hold in your hand a little light clock. It will bounce just, of course, light travels really fast. So if you're moving at everyday speeds, you don't notice that. But if you move, but in principle, it is there. Your time will slow down a little bit compared to the person who is not moving. What's actually interesting is the same thing actually happens in reverse, because if you're on a train, like I said earlier, you don't know that you're moving, and you think that everyone else is moving backwards if you look out the window. And you'll see this is where just the crazy effects of relativity comes in. It's that according to you, everyone else's clock that's moving backwards are going to run slower because they are the one moving, and you think you're sitting still. So now, so that's we realized that is a real effect, and I'll talk about how some of the cutting edge experiments actually have been verifying that. But let's go back to the concepts and the theory and think about, does time slow down enough? This is actually the formula that Einstein figured out by calculating how much slower that clock will run. So don't worry about exactly how that goes up. So that's a little bit of algebra. But it turns out that the time does not slow down enough in that earlier picture. So the answer is no. And what needs to happen is the whole concept of distance needs also to change. The idea of length needs to change. So if we go back to our previous example, what happens is this does not actually slow down. The time of the moving spaceship does not actually slow down all the way to 6 seconds, right? So when this guy's clock run for 12 seconds, one can actually run the numbers. It actually only slows down to 10 seconds. So we still have a problem. And the resolution to that, Einstein thought, is, well, what if distance also change, right? Maybe instead of when this guy is moving, his ruler is not that long. It's a little bit shorter, right? So instead of measuring 6 light seconds, his ruler being a little bit contracted, a little bit shorter, has measured, well, that will take me 10 rulers, 10 of these little light second rulers, because each light second, each distance, the whole idea of distance is shortened. And that will give me the right formula where the speed of light is now measured by 10 light seconds over 10 seconds and will give me the correct speed of light. Now, so what have we learned? When something is moving, time will slow down, distance also gets shrinked. All right, so I'm not going to go too far into the nitty technical details, but let's just ask the question, well, all right, this thought experiments with spaceship all sounds good, but does it really slow down? I think that's what everyone's in your heart is really asking. Does it really slow down? So this was one of the first experiments that was done. And the answer, well, spoilers, is yes. This is one of the first experiments in 1971 by these two guys who took a cesium atomic clock. So it was one of the best measuring devices, time measuring devices back in the day, and took it on a commercial airline and flew around the Earth twice. One in this towards the east, one towards the west, and compare it with, they put 4 atomic clocks there and 4 atomic clocks on the ground and 4 atomic clocks to the other plane, and compare the difference back over here. So after they flew for however many hours, come back, they check with this clock on the floor and check with the plane that's going on the other direction. They all actually measure the difference, and the difference is exactly as predicted by Einstein's formula when he just figured it out with just basic trigonometry using the light clock. How amazing is that? This measured if you are on a plane, you move at some speed, even in a commercial airline, you can. It's a very tiny amount of time difference, but it is there. Now, you might still think, okay, maybe it's the airplane because it's taking off, landing, it's moving up and down, there's turbulence, is something bumping the clocks, is something affecting the experiments, is it just a huge coincidence? Well, there's another experiment which involves what's called muon lifetime and muon decay, performed many, many times. So what is this? So muons are just some cosmic ray particles that is produced by the sun, and it's caused by this protons from the sun. So the sun will eject a lot of particles to our atmosphere. And when a lot of the atoms and protons hit our atmosphere, these high energy collisions starts creating these muons. It's basically another particle, a very subatomic particle that is just 200 times heavier than an electron. So it's basically a little bit like the heavier version of an electron. It's a particle. And it creates this particle in our atmosphere. And when you create these little, so it's usually denoted in particle physics using the symbol mu. When it's created in our atmosphere, then they'll start streaming down to us. They're really light, it's just like random electrons, a little bit heavier than electrons, but doesn't cause too much harm. But what's interesting is these things, when we create it in the lab, we know that they have a certain lifetime. And in fact, a very, very short lifetime. They decay after a couple of nanoseconds. Very, very short lifetime. All right. So if you create it, then it just decays and becomes something else completely. And we know exactly where in the atmosphere these things will create, at what heights they will start hitting the atmosphere, and that the cosmic rays will start hitting the atmosphere and start creating these muons. And then they'll decay in a couple of nanoseconds. It's really, really quick. And you can do a calculation that even if it travels at the speed of light, there's no way it will reach the ground of the Earth. So if I set up an experiment to detect for muons, if I set up a device to capture the muons from pointing it to the sky and hope for some to capture these, in principle, because they decay so fast, there's no way they will reach the ground of the Earth, right? However, when these experiments were done, they actually found a lot of muons. They actually found a lot, much more than one would expect. How is that possible? And that's precisely because how fast these guys are moving, close to the speed of light, their time slows down. So their decay actually slows down. So the lifetime, the 1 second for them, let's say they're supposed to only take 2 nanoseconds to decay, but their 2 nanoseconds is slowed compared to us. So when we measure that, it'll take much longer for it to actually, and it'll give us enough time for it to reach the bottom of the ground of the Earth when we measure it. So not only time is affecting clocks, like mechanical clocks, it's affecting the fundamental nature of whether unstable nucleus and unstable particles decay. It's literally time itself that's slowing down. It's not the gears that is running slower. It's not some sort of mechanical thing or even a biological reaction that's slower. Literally, time is slowing down, right? So personally, when I heard of this, I've never heard of something so crazy. Hope if this is the first time you've heard of this, hopefully you feel the same. And this is such a wonderful, amazing thing that I rarely know about how the world works like this before. Anyway, all right. So after all this, how does this relate to our initial question of the sheep? Well, we had this question of, well, all right, so do the speeds just add up when things are moving like this? How do things fit together? So it turned out the idea is the age-old wisdom of we just adding the 2 speeds. If we add up the 2 velocities together, that is not correct. If we want to find out the speed of something relative to something relative to something, you do not just add them. And Einstein figured out the right formula. So obviously this is not a whole math class, but I'll just sort of show you. After all, this is from the mathematics department, the School of Mathematical Science. So just show you some formulas. Usually this is a no-no in any public talk. You should never show anyone any formulas. But hopefully this audience, I trust that it is okay. And some of you, if you were like me, just want to know a little bit more about the formulas. And if you're interested, hopefully this will give you a little bit of insight. If you really have a phobia with formula, don't worry. This will be over in 60 seconds, according to my time. So this is the actual formula that Einstein discovered that you should do when you add up velocities. You notice that the age-old wisdom is still there, but then there is a bottom part, a denominator in the fraction for the correct formula in order to fix this, right? So what would that entail if anyone is actually curious in plugging in the numbers? So one of them is moving at a speed of 2 meters per second, the other is moving at 2 meters a second. All you have to do is plug this into this formula, and c is the speed of light. So you will plug that in, plug in the calculator, and you realize that it is not 2 plus 2 is not really 4. Well, 2 plus 2 is 4, but when you try to figure out how fast the sheep was moving, when it's moving on top of a moving truck at the 2 meters per second, then what you will see is not actually 4 meters per second. It's just so much, a little bit less than 4 meters per second. Right? So this is the truth. Even though it's a tiny bit, it's actually detectable, and it's tested over and over and over again for the past 100 years in science. Einstein published this in 1905, and we're over 100 years since his discovery of the theory of special relativity, and this has been tested and nothing has been, any experiments have violated this prediction so far. Right. So again, if anyone is curious, why do we even think this in the first place? Just for those who are interested in a little bit more mathematics, just to push this a little bit further, you see that it's all because of the c square over here is a huge number, because the speed of light is 3 followed by 8 zeros, or 3 times 10 to the power of 8 meters per second squared. So actually, that's 9 followed by 16 zeros. So we have a very, very small, very large number over here, which means this fraction is whatever number that your normal speeds in your everyday life are. If it's smaller than that, well, this is going to be a very, very tiny fraction. And that would be almost equal to 0, well, which this was basically the reason why in what we usually, in everyday, we just think that, oh, speeds just add up. All right, so hopefully that was a little bit, if you have never heard of these ideas, hopefully you found them interesting. If you've heard of these ideas, hopefully the little bit of formula gives you additional insight into some of these concepts. So just to summarize everything we have sort of introduced today, first of all, when things are moving fast, velocities don't simply just add up. That's one of the shocking things. And there are 3 things that will happen. First of all, your time actually slows down. It's very real, measurable. Second thing is called length contraction, where your length actually contracts. The third thing we haven't really talked about, but it is there just for completeness. I'll tell you the mass actually increases as well. So things actually get heavier and heavier when the closer and closer you move to the speed of light. In fact, if you go towards the speed of light, your mass will increase towards infinity, and you have to pump in almost infinite energy in order to go to the speed of light. And that's why you can actually never achieve the speed of light and reach that. And in all of these things are actually real physical measurable effects that has been tested over and over again. All right, so this is the end of basically everything I'd like to share with you. Hopefully you have enjoyed it. I really want to thank you for watching and listening to this. We'll move on to questions and see if you have any questions. Feel free to type in the comments and let me know. So I'm just looking at the comments at the moment. I haven't seen anything just yet. Have you ever heard of special relativity? Are these some of the things you have seen before? Okay, I was also told that there will be a couple 30 seconds of delay as well between the comments. So I'll just check if there is no comments. We'll wrap up in a bit, but I'll just give a few more seconds. And if the host can let me know if this is also, if the comments are live and it's running, that would be good as well. All right, so it looks like everyone completely understands special relativity. So this is good. In this case, thank you very much for coming on a Friday afternoon to listen to mathematics and physics talk. Hope you enjoyed it. So before you go, I'll just like to ask you to help us to share your thoughts about today's live stream and what we can do to improve for future live events. And thank you for taking part in this. So if you can go to the QR code on the screen or visit the link on the screen to fill out this very short anonymous survey. That would be really good. And don't forget that this event is part of the long program of the Southampton Science and Engineering Festival, also known as SOTSEF, starting today, Friday the 11th, and it will run all the way through next week until the Saturday, next Saturday of 20th of March. So check out all the events. If you want to know more about it, book free tickets and save the date in your diaries for other live events. Please go to the website of sotsef.co.uk. All right, thank you very much, and hope to see you in the near future.